Yeah, hi everyone, I'm Ed. I'm a research fellow at CVSSP, and I'm working in Rich's group, who's over there. Do you want to give a wave, Rich? Hello, hello. Our group is a cognitive vision group, and we work mostly on sign language translation and production. And in this paper, I was exploring how to create good representations of sign language to be used with LLMs. Okay, so it's actually quite difficult. I'm going to show you some examples of sign language, and hopefully they'll show why this is difficult. So if we look at this first sign there, should we do it again? Okay, we've got finish. Okay, let's look at another sign. And we have finish. So we've got two signs, the same meaning, but they've got different hand shapes. Let's look at the third one. So we got the same hand shapes again, but did you notice the lip pattern was different? This one is complete, okay? Let's look at one more. Any guesses what that is? It's not finished, it's fantastic. So what we can see here is how difficult it is to create these good representations. If we were going to embed these with like a clip model, for example, what's going to happen is they're all going to kind of cluster together, right? And we're not going to be able to differentiate between each one of these signs when we ingest it into our sign language model. Now, obviously, the answer is probably more data, but unfortunately, in sign language, we don't have a lot of data available. Some of our largest data sets are about 1,000 hours, and when we compare this to video data sets that we use to train video models, they're about like 134,000 hours. Okay, so we can't necessarily get better representations just from creating more data. So how can we do this? Okay, well, let's look at the skeletal representations of some of these signs. And what we can notice is if we break these up, they have a kind of hierarchical structure in terms of the amount of information that they portray. So, for example, the arm movements, we can consider these as like a higher level node. They don't carry that much information, and there's kind of a limited range of how many different arm combinations you can have. But the face and the hands, these become like a lot more difficult. There's a lot more intricate variations which can dramatically change the meaning of the sentence. So if we kind of model this like a bit like a graph, we can see, like as we were saying, we have our arm poses here. These ones are quite easy to distinguish from each other in a like Euclidean embedding space. The faces, they're going to be slightly more difficult, and the hands, they're going to be really difficult unless we have lots of data available. So in this paper, what we're looking at is how can we change, rather than trying to improve these embeddings, how can we actually change the underlying geometry itself so that we can create more space for these fine-grained hand details? And we can still use this kind of Euclidean space for these larger body motions. And one solution to that is hyperbolic geometry. Now, hyperbolic geometry has these really nice properties for these kind of tasks. And if we look at this crochet, basically what we're doing is we're doing a ring of crochet, and then we're adding stitches as we go around. And as we add these stitches, we get exponential volume growth as we approach the perimeter of the hyperbolic manifold. Okay? So, and if we project this down into a tangent space, we can kind of see here that these lines actually represent the fastest way to travel between 2 points, or the smallest distance. So, for example, the point to here, if we went this way, we'd have to go all the way around this hyperbolic geometry. It's actually faster to go into the center and back down. So why is that useful for our task? Well, what if we could take our poses, and in some way we could project them onto this hyperbolic geometry? We can push these hands to the edge of the geometry, and now we have lots of distance between all of these hand features. These are going to give us better representations to then shove into our LLM and create our translation. Okay, so first of all, I'm going to show you the basic setup for a sign LLM, and then I'll show you how we can inject this hyperbolic geometry to improve the representations. So if we split up our poses, we're going to run them through STGCN, and then we're going to have these embedding representations of the face, the body, and the hands. Next up, we can just concatenate these. Then we can apply some convolution. That was a lot slower than I was expecting. These then become our embeddings, and then we can pipe these into our LLM, as I'm sure you're all familiar with. We do our magic. Okay. Now, what we want to do here now is we want to somehow create some regularization scheme where we can take these Euclidean embeddings and we can inject this hierarchical hyperbolic geometry. So the way we're going to do that is we're going to add this exponential map from the embeddings. What this is going to do is it's going to project these embeddings onto the hyperbolic geometry. We'll do this for all of our embeddings. And then what we're going to do is we're going to take our text embeddings from our language model, and in this case we used MT5 base. We'll take some language embeddings from one of the final layers of the model. We'll apply the same exponential map, and then we'll have some representation in the hyperbolic space of the text. Okay, and now we need to learn some things. So what we're going to do, first of all, when we perform our exponential map, we're going to have some learnable parameters, and these are going to decide where we position these features inside the hyperbolic geometry. And then what we're going to do is, because we need to minimize the distance between these poses and this text in a contrastive learning setup, what we're going to do is we're going to actually find the mean of these features. But when we compute this mean, we're going to weight it. And the way we're going to weight it is we're going to measure the distance between these features and the center of the hyperbolic geometry. And if you remember, the center of the hyperbolic geometry is basically Euclidean. So if the features are closer to the edge, it means that the model wants more space in order to pull them apart from each other. Okay? So then the mean of our features is going to move across closer towards the edge of the features. And then we're going to do like info NCE loss. But the difference is we're going to take the negative hyperbolic distance between the pose representation and this mean pose representation and the text representation. And obviously that distance is going to be curved along this hyperbolic plane. And we're going to minimize this distance. Okay, in the paper we actually introduced two methods to do this. I've just explained this pooled method, which is a slightly like simpler method and a lot more computationally efficient. In the paper we also present a token method, which actually performs the hyperbolic tension, where we can look at all of the individual text tokens and map them to all the individual pose tokens. But I won't explain that for time, but you can read about it in the paper. Okay, so what does this embedding space look like? Well, after we perform this regularization, what we can see is these blue circles here, these are all these body poses. And the model doesn't need to use the edge of the hyperbolic geometry to represent these because they're all quite different from each other, right? The face, this requires more of the curvature of the hyperbolic geometry in order to separate the features. And the left and the right hand, these have been pushed right to the edge of this Poincare disk, right? So that means that the model is learning that, okay, these features are too close to each other, they're too similar, I can't decide between them. We're going to push them out to the edge where they're going to have a lot more room. We can create hyperplanes between them, our model's going to be more robust, and we'll get better results. In this figure, what we can see is this is the center. 0 is the center of our hyperbolic geometry. So this is the Euclidean part of our geometry. And what these bars represent is they represent the model training and how it's pushing these features into different parts of the geometry. So we can see that the right hand is being pushed further to the edge of the Poincare disk there. Okay, so does it work? It works a bit. Like, it's not amazing, I'll be honest, but but it does work. So this is our kind of baseline. You'll notice that many of these methods are using RGB features. And we're only using the pose features. This is useful because in sign language, we don't have, like in our data sets, we might only have a handful of signers. And also we might want to be privacy aware as well. So there is an advantage to using just pose. So if we look at the baseline for the state-of-the-art pose model, we have a free rouge score improvement. And we have like a modest improvement in blur 4, which means that we can basically predict 4 words in the correct order. In this example, we use the Chinese Sign Language data set. And we can see in the center here is our approach. And this is the state-of-the-art method. And if we look here, we can see that we actually, if we look at the exact match between the verbs, we can see that we have an advantage over some of the other approaches. So we're able to get more detail out of our translations. here we've got a representation of one example. So on the left-hand side, this is the Euclidean example. And to obtain this, basically what we did is we performed the same hyperbolic regularization, but we set the curvature of the space to 0. And so it's basically Euclidean space. We can see that all of the hand, body, and face tokens, actually the body's slightly separated for some reason, all clustered together. And these are the attention between the characters. When we perform the hyperbolic regularization, we can see that the body is in the center of this Poincare disk, and the hands have been pushed to the edge, and we have a better balance of the attention to the text tokens. Now, one of the really nice characteristics of this space is that it's much more robust to noise. And that's because when these hand features have been pushed to the edge, there's more distance between them. And if we have perturbation in the pose estimation, we can still clearly distinguish these poses from each other. And so that's what this experiment does here. So our method maintains higher accuracy as we add this additional Gaussian noise to our poses. Okay, there's a very brief summary. For more details, please read the paper. And also, I'd just like to quickly plug an event next month that we're running here. It's exactly the same setup. Rich will be speaking, giving an amazing presentation, I'm sure. Professor Andrew Zisserman will be here, and an academic from Gallaudet University. It's on sign language translation, production, and linguistics. It'd be great to see you all there. You can register on the same website that you registered for here today. It'd be good to see you. Okay, thank you very much.
Take a couple questions.
Hi. Yeah, great presentation. Apologies if I kind of missed the point on that. But the when you were calculating the mean of all of the different poses for each feature, right? Yeah. Did you ever encounter any problems with collisions, right? As in, because the left and the right hand are on opposing ends of the space, would an approximation that is slightly different and mean a slightly different thing cause a collision of the mean?
Oh, right? That's a really interesting point. So I actually have the algorithm here for computing the weighted Fresho mean. Mm-hmm. It's like an optimization, and it has a unique solution. Mm-hmm. I haven't actually checked for this collision, but it's interesting. Maybe it has occurred and I didn't notice.
Yeah, because it would be interesting to see the collision rate of the mean method, right?
Yeah.
As opposed to the unique method, which I imagine would collide less because it's distributed over a wider space, right?
Yeah, absolutely. Yeah, that's a really interesting point. Maybe you can explain it to me in more detail later so I understand it better.
Yeah, fair enough.
Yeah, for sure.
Yeah, so really interesting. I'm kind of interested in hyperbolic learning for video. And I'm just wondering, you mentioned the two different methods of learning. You have just the contrastive one where you just project and then you drag them.
Yeah.
And then you have the more end-to-end hyperbolic method. Do you have any insight as to when you would bother using the second one versus just the simple contrastive one?
That's exactly what the reviewers asked.
I think it's kind of interesting because presumably you have to throw away your weights if you're training hyperbolic modules.
I see what you mean. If you pre-trained it one way, or
so if you took clip or something,
right?
And
okay.
then you wanted an end-to-end hyperbolic.
I
clip.
get you.
Yeah.
Okay, yeah. So exactly, this is something we explored. So we took the original network, and then we injected using this contrastive regularization. And the reason why we didn't do it end to end is because of this reason. And if you see, the forward latency. When we add the hyperbolic method, we got a 200% increase. And this is with the regularization approach. So we can actually only really train, include this regularization for a small amount of fine tuning afterwards. And I have actually implemented this end to end, and I can't train the thing because it just takes too long. And there's a few reasons why. The first one is we can't train hyperbolic in mixed precision.
Yeah.
So you can't use all these nice tricks, essentially. Yeah. The other thing is we have to keep performing exponential and tangent maps, and those are quite computationally heavy. So it just basically slows everything down. The pooled method is one way to kind of get around this. We have a slightly smaller increase. when we actually perform the attention in the hyperbolic space, things go really bad for us.
Yeah.
The performance is better, but yeah, 500% increase in latency is not very nice.
Yeah.
Yeah, but it is quite, in terms of memory, it's very efficient. We only add, we barely add any additional parameters to perform this, so it has some trade-offs, yeah.
Cool.
Yeah,
Thank you.
no worries.
Yeah.
I guess another the last question. Yeah.
Try to plug it back in. Okay.
I noticed that you had consistently larger feature norm for the right hand than
Yes.
the left hand.
Yes.
Do you have a conceptual explanation for that?
Yeah, I think like a lot of the sign languages, the finger spelling is on the right hand, and there can be a tendency for, if you're a right-handed signer, like many of the signs kind of lead with the right hand. Some networks, what they do is they essentially just fire in the embeddings and they just flip them, like an augmentation technique, and that would kind of balance that out. But in this method, it just didn't do it.
Okay.
Yeah, no worries.
So thanks for
Thank you.